So welcome back to the course Learn Blockchain. Today we will be talking about an interesting topic called Byzantine fault tolerance. It is an important topic not only for blockchain but also for decentralized system. So we will understand about the Byzantine fault tolerance with the help of an example. Here we have a castle, then we have 4 generals surrounding the castle from each direction. These generals are here to conquer the enemy's castle. And there is a catch. These generals will win the battle if all the generals attack together. Even if one general decides to retreat, then they won't win. So in order to get victory, all generals must attack together. Or they can retreat too, which will prevent them from losing the battle. And among these 4 generals, one general is traitor. But the decision here to attack or retreat is made by majority. If majority favors the attack, all generals must attack. And if majority decides to retreat, all generals must retreat. So we need to create such a system that even if there is a traitor, it won't impact the decision. Basically, we need a method of agreement among the generals. And here we have the Byzantine fault tolerance. According to this method or algorithm, we can have a decision that will prevent us from losing the battle. These generals can communicate two-way with one another, like these arrows. Now let's understand how it works. Among these 4 generals, one is the head that provides the command to either attack or retreat. Let's assume this one is the head general and he is not a traitor. We will also look example of head general being traitor. So for now, let's say this one is the traitor. Since the head general sends command, he doesn't need to receive message from order. So we can remove these arrows. Now let's say the head general sends attack message to the remaining general. All these remaining generals will receive attack command denoted by the green arrow. So for the consensus, that is agreement for decision, it is done like this. Those who receives command from the head general communicates with each other and say what the command was from the head general. So this general, since he is not a traitor, he will say that head has told me to attack to other 2 generals. Similarly, this general will also say head has told me to attack, but this 3rd general, since he is a traitor, he won't say head has told me to attack. Instead, he will say head has told me to retreat. So after exchanging these messages, the decision is made through the majority. So the head general, since he issued the attack command, he will favor the attack. Then this general, if we see here, he got 2 messages with attack and 1 message with retreat. So he will favor the attack. Similarly for this general, he got 2 attack messages. So he will join the attack too. So here already 3 generals decides to attack. So as per the majority, all generals must follow the majority decision and they will all attack. The same will be for the retreat message if the head general had sent retreat command. Now let's see what happens if the head general himself is a traitor. Would our algorithm still work? Can it maintain the fault tolerance? Okay, so if the head general himself is a traitor, he won't send the same command to the remaining generals. If he send attack command to the all general, then all of them will easily agree to attack. And same goes for retreat. So he will send one command to one general and another command to another general. Let's say he send attack command to this general and retreat command to other 2 generals. Now like previously, those 3 generals will communicate with each other. And it will be like this. Red arrow denotes the retreat command and green arrow denotes attack command. So for this general, he got 2 retreat and 1 attack messages. So he would go for retreat. Similarly, this general also receives 2 retreat and 1 attack message. So he will also go for retreat. And also for this 3rd general, he got 2 retreat and 1 attack message. So of course, he will also go for retreat. Now here the majority is for retreat, so the decision will be retreat. And all generals retreat. So this way, they do not lose the battle. If head general had sent 2 attack and 1 retreat message, the decision would have been attack. So still our algorithm is fault proof even if the general is traitor. Hence this is Byzantine fault tolerance. I hope you had understood it. Now the question will be, how much is this algorithm tolerant? To what extent? What if we had 2 traitor instead of 1 in our example? For 2 traitor, there is no way that the algorithm will succeed. You can try it on your own. The algorithm won't remain fault tolerant if we had 2 traitor among 4 general. So it means that there is some limitation in this algorithm. There are mathematical calculations for this, and the conclusion is, in order for this algorithm to work, there cannot be more than 33% traitor among the whole army. That means this algorithm works only if the number of traitors are less than 1/3. So in our example, we have 4 generals, so we can only have 1 traitor. If we had 10 generals, then we cannot have more than 3 traitors. So this is the level of tolerance of this algorithm. Now you might be wondering, how does this come into the blockchain or other decentralized system? So in the blockchain, if someone tries to attack the system, we need some kind of consensus protocol like an algorithm like these generals come up in our example, which we will discuss in the next video. It will allow us to protect the system from traitors or hackers. So we need our system to be more fault tolerant as possible. The concept behind the Byzantine fault tolerance is this. So this is all about the Byzantine fault tolerance. If you want to learn more, I will suggest you this original paper on Byzantine fault tolerance. Check the description for the link, and on this note, I will see you in the next video.